This video will explain our latest project, KerasBERT, modeling the Keras language. As a quick background of what motivated our interest in this project before getting into the technical details of it, we were really inspired by OpenAI's Codex model. OpenAI's Codex model is a language model that's trained on GitHub code data such that it can perform these kind of code completion tasks where you have this natural language interface to create things like web apps and all sorts of different applications that are available by importing some kind of instructions in natural language, and then OpenAI Codex will generate the code, in this case JavaScript code, to create some kind of a space blaster kind of Atari style game. And you would write something like make it be smallish in a very casual natural language, and now OpenAI Codex will fill out this CSS code in JavaScript as it appends this 100 pixel width onto the image of the spaceship. So this OpenAI Codex thing was a really exciting inspiration for us to think about what we can do with these language models and our own code data that we're using to develop kind of computer science applications in general. And then also there's been an incredible new source of information with Keras code examples. PyTorch examples similarly has started populating community contributed examples of all sorts of contributions and interesting applications like consistency training, cut mix, supervised contrastive learning. All of the cutting edge things are now being contained in these Keras code examples that show you how to do it for yourself. So this idea of maybe combining this Codex functionality with this kind of data set is the high level motivation of why we want to investigate what we can do with KerasBERT. Here's an overview of our presentation of KerasBERT. We'll start off with some technical background of language models and the text-to-text transfer transformer, as well as the key difference between working with text data like what GPT-3 uses and traditional natural language processing applications compared to working with code data, as well as these blends between natural language and code data sets. Then we'll talk about how we built the Keras docs data set and what we're considering with the future for maintaining these kinds of data sets. Then we'll show the learning curves of fitting our language models on this data set, and then we'll get into how we try to evaluate this model with closed task completion, and again looking at these learning curves, and then comparing it with the GPT Neo 6 billion parameter model with the zero-shot inference, and some ideas we have for the future work of developing KerasBERT. So here's a graphic overview of the concept of language modeling. Language modeling generally has two forms in the literature, where it's either structured as a denoising autoencoder, or it's structured as you're always predicting the rightmost thing at the end of a sequence. So this picture is taken from OpenAI's task of applying these models to images with Image GPT. This is a very common practice in natural language processing, and I think understanding that how they were able to take the same modeling framework to images will help you further understand the generality of the setup of autoregressive modeling, or BERT's denoising autoencoder modeling. So autoregressive modeling is, say you have time series data like stock prices over time, and you want to know what the stock price is going to be on Friday, and you have data from Monday to Thursday. That's kind of the high level idea of what autoregressive modeling is. And so for text, what it means is, say we take image taken from generative pre-training from, and then we predict pixels. That's the idea of autoregressive modeling. Whereas BERT is you're masking out intermediate words from the sequence, or just intermediate anything from the sequence, whether it's the stock prices example again. Say you mask out Tuesday and Thursday and you have the Friday information, but you want to recover what happened Tuesday and Thursday. So we're using the BERT idea for modeling Keras because we think this intermediate bidirectional context compared to just the left to right context is more useful for applications like debugging deep learning code, where you probably have the whole skeleton of what you want to do, and your error is probably somewhere in the middle of your code rather than definitely at the very end of your code. Another recent trend in language modeling and natural language processing that inspired our interest in this framework is the text-to-text transfer transformer. What this shows is the effectiveness of transfer learning by just providing a description of the supervised learning task as a prompt to the language model. So if we want to autocomplete code, or we want to debug code, or we want to do machine translation from, say, Keras to PyTorch, we could just append the supervised learning task description and interface it directly with the language modeling setup. So this is a new breakthrough in the generality of this kind of language modeling framework, and so we feel like we can really build a lot of supervised learning functionality onto this base core of our language model. So now we'll get into the difference between modeling text or language data compared to modeling code data. So the first key question we have is where we can find code data at scale. So language models like GPT-3 or the T5 model, they're trained on massive amounts of text because they're able to scrape things like Wikipedia or books or Reddit, and they're able to get these massive data sets of text, and big data sets and big models really work well together with these deep learning techniques. So one answer to where we can find code data is generally GitHub. GitHub is generally the best place to find it, but there are other examples like these competitive programming or interview coding platforms like, say, LeetCode and Codeforces. Those are also that has also been a good source of data. And increasingly, we're seeing, say, Keras code examples and the PyTorch examples. We're seeing more and more tutorials. Things like Medium is also a great source. Stack Overflow. So we're looking to see where we can find this code data, and that's another active part of this research. And then the next question is tokenizing text versus tokenizing code. So tokenization is a huge part of what makes these natural language processing pipelines work. That's where we split up the words into atomic tokens, and then we map those tokens into a continuous embedding table. So in deep learning, we have continuous embeddings for categorical variables. In this case, we have a high cardinality set of, say, 30,000 tokens that we break up our text data into and then map them into their index in some continuous embedding vector that might have a dimensionality of like 128 and 256, compared to that one hot encoding that you might use with something like a bag of words way back in the day before these deep learning techniques. So then another key detail about this, though, is the natural language code datasets. Most of these code datasets, they're not all code. It's a hybrid between language and code because most people either comment code on GitHub or they're written in tutorial style, where you have alternating blocks between natural language description, code, natural language description, and so on and so, and also the outputs of code. So you have this kind of multimodal data set between natural language and code, where they both do look very similar, but they are different kinds of data. And then the question of transferring models from text to code. So we'll save this for our results, but we're curious about this idea of starting off from, say, a Glue or a Squad or one of these language data sets. If starting off from that, if you train that successfully with supervised learning, can we then transfer that to the KerasBERT modeling, and will that general language understanding ability that it starts with help us with our code modeling? And to fast forward, the answer to that is no. But so here's the general things to thinking about when you're thinking about working with code data. And generally the biggest challenge is tokenizing it, because in code you have things like these parentheses, you have these long chains of chaining together the different like methods and class names and things like that. So it's harder to just break it up with, like, spaces is generally the heuristic that you use to chunk up words in language. So we need different kinds of heuristics to kind of break up these code units, to break up like methods and arguments to methods and things like that, in order to tokenize this as successfully as language is tokenized. So the first step in modeling KerasBERT is to build the data set to use. So we start off with the keras.io website, and we scrape the Keras code examples, which make up about 64% of our data set, the Keras API that describe the different classes and methods in the classes for all of the different layers and models and optimizers contained within the Keras deep learning Python framework. Then we have Keras developer guides. Similar to Keras code examples, these are a collection of tutorials of how to use the API, whereas the key difference between the developer guides and the code examples are the code examples are end-to-end examples like point cloud classification or CT scan classification, whereas Keras dev guides are more like short examples of how to compile a model or how to write a custom loss function or how to write a custom train step with accessing the gradients in the Keras framework. We learned a lot about the performance of these models by studying the learning curves. We start off on the far left by using all the data and creating IID train test splits. We have the training and test data are sampled from the same data distribution of using all the data, and in this case we have this the curve that we'd like to see, where the training loss decreases and the validation loss, the test set, continues to decrease as well. However, this setting is the IID train test splitting, where we have independently and identically distributed train test sets. But in the real world, generally we don't have the test set sampled from the same distribution as the training set. This is commonly referred to as distribution shift. So in this case, we're studying domain generalization as the subcategory of a kind of distribution shift, where we switch from, say, the Keras API guides into the new domain of the Keras code examples. So what we're doing in these three curves is we leave one of the sources of data out of the training set. So when we do Keras developer guides left out, we train on the Keras API documentation and the Keras code examples, and then we evaluate on the Keras developer guides. So the test distribution is now different from the training distribution, and this is a common thing that we see in the real world with recent data sets like the Wilds benchmark, really outlining this phenomenon of distribution shift and why it's such an important focus for deep learning compared to just IID evaluation. So we see that in the case of using these test distribution shifts, we no longer have this monotonically decreasing error with both the training and validation error. So we need some new techniques to try to continue to decrease the test loss as we continue to decrease the training loss. In addition to looking at the test metrics, a common practice to evaluate language models is to visually inspect closed test completion. So we start off with the input. The mask class groups layers into an object with training and inference features. This is referring to the Keras model object, the model class, which groups the Keras layers or the deep learning layers like convolution and multi-layer perceptron into the object of the deep neural network, and then has these training and inference methods to use the Keras deep learning framework to train models. We see that our model is able to correctly predict that model is the right continuation of this sequence, and we test several other such completions. In this case, we test its knowledge of the callback function within these Keras models, and then we also test a more specific thing where it doesn't perform it well. But in this case, we're looking into a very specific inference within the deep learning literature itself. The reptile algorithm was developed by OpenAI to perform model-agnostic meta-learning. Specifically, this algorithm is designed to quickly learn to perform new mask with minimal training, few-shot learning. So in this case, as humans studying deep learning, we can probably infer that it means new tasks because of the few-shot learning context. This is another example of how the BERT bidirectional context of having the left context and the right context may help with these kind of completions as well. So we see that our model does put some probability density, in this case more so than the all data model, but it does put some density on tasks, so it has kind of learned to make this inference. So this is a pretty interesting case where in the first set of inferences, we're directly copying and pasting from the training set just to see what's happening. And then we also constructed something around 200 paraphrases, manual paraphrases of these kind of questions to see what that did to the model as well. And we'll show the results of that later on when we compare this model with the GPT-NEO model. So before transitioning into our comparison with the GPT-NEO 6 billion parameter model, we were very interested in the idea of fine-tuning from natural language to these code datasets, which are really more like natural language and code datasets. So the general idea of transfer learning is to learn one task and then transfer to another task, and pre-trained checkpoints of natural language processing models that have learned some task are everywhere on the Hugging Face Model Hub. So we thought that we'd use the pre-trained weights from language modeling, the Roberta model, which is the same architecture we use for KerasBERT, to see if the initialization from some natural language processing task would help us with the KerasBERT modeling. And we think that the main challenge with this is the tokenizer gap, because you have this difference in tokenization from the character distribution or the, say, n-gram distribution between language and code, that I think that gap is what creates this lack of transferability. And it's also worth noting that OpenAI Codex and OpenAI, they tested this on a very large scale with something like a 10 billion parameter GPT-3 checkpoint, and they also didn't find that this fine-tuning helped with their model. So here's what we find. We find basically the same learning curve from scratch and fine-tune, and we're also evaluating with all the data with IID trained test splits, but this is just showing the train loss decreasing, which generally find this trend for all the evaluations. And then here's a case of the inference as we look into the fine-tune and from scratch, and we find really that the from scratch model generally just we think it performs a little better than the fine-tuned model. So we were also very interested in scaling up language models, and luckily for us, GPT-NEO 6 billion parameters is an open sourced endpoint where you can test out inferences in zero-shot learning by accessing this web demo at this link, 6b.eleuther.ai. And we've accessed this as recently as November 2021 to assure the demo is still working. So what we do is we put in some inference here, and then we run the model with the top P and temperature hyperparameter, although we don't tune these hyperparameters because all we have is this web demo inference. We haven't loaded the model into our personal runtime, although you can do that. So GPT-NEO is trained on the pile. So as you see this composition of different things like PubMed Central, biochemical research papers, archive, all sorts of research papers, things like, say, books. We have this gray square rectangle is the GitHub portion of the GPT-NEO training data. So GPT-NEO has seen things like TensorFlow and Keras in its training data, and it's very obvious also when you query it that it has this kind of knowledge. So this is the composition of the training data used to train GPT-NEO. So figure 6 is showing our comparison of the GPT-NEO model with KerasBERT, and there are a few other things to note about this kind of comparison. So the first of which is these are our manually crafted test sets. So we've constructed 200 paraphrases of things in the training data, so they aren't exactly in the training data, and this causes a massive performance decrease for our KerasBERT model. The second thing is salient masking compared to rightmost masking. As mentioned in the very beginning of the talk, our KerasBERT model can model context bidirectionally, whereas these GPT models are autoregressive models, so they only predict at the very end of the sequence. So that's one of the difference between these closed tests, as we see where we put the mask somewhere in the sentence, is that with GPT you always put the mask at the very end of the sequence, whereas with BERT you put it in the middle of the sequence, and we personally think that BERT is going to have more generality for these kind of coding frameworks because we imagine the bidirectional context to be more useful than the left to right. But we think the main story of this performance boost, obviously, 58% compared to 4% top one is a massive improvement. But we think this is mostly due to the size of the model. So we think it's mostly having the 6 billion parameter models rather than the task setup. We think this is something that we'll need to continue exploring in future work. But this is the comparison of the rightmost masking GPT-NEO model performing much better than KerasBERT. And again, GPT-NEO has just been trained on this square of GitHub, and then it has this kind of general language understanding from all these other data sets, from legal data sets to, again, biomedical papers, just books in general. So it's an extremely interesting data set, things like YouTube captions, Hacker News articles. It's a very interesting composition of data. One of the most interesting trends in exploring things like these pre-trained GPT models is to add some kind of prompt to the input. So we're inspecting one of the answers that our GPT-NEO model got incorrect. This is the summary method of the model class raises a value error if the summary function is called before the model is and the ground truth answer is built. So without any prompt, it says fitted. If you want to check the summary methods of the different models before calling fit or predict, then you will need to filter out the appropriate ones yourself. This is generally not recommended though. So the interesting thing about this is this phenomenon of hallucination in language models. So what it's writing, it kind of makes sense, and it's using things like fit with the empty arguments that are impressive and make you think it knows what it's talking about. But this is nonsense, this answer. And the fitted thing is kind of on base, but really you don't have to fit the model before you call the summary. So it's not a true understanding of what's happening with this. So we did try to prompt it to see if this would maybe guide the generation better. So what you do is you prepend it. So the input is information about the Keras programming language. The summary method of the model class raises a value error, and so on. And other things like question about the Keras programming language, and then you add this, and then you say what at the end. And this kind of thing might help it remember like a Stack Overflow question that it saw in its training set. And we see it as you turn it into a question, it goes, thank you very much for the clarification. It has to thank the question asker as you would see online, and then it gives the answer in this kind of format. And you see the import TensorFlow as TF. You see that clearly it's memorized some of these interesting things that, I mean, this code would probably compile and run, assuming it had this model path in the directory. But generally what it's saying makes it's like it's remembering the things, but the composition and the common sense of it does not make sense. So we view our KerasBERT model as a foundation for this kind of research, and we have a lot of ideas for future work on this. We're really excited about the idea of using data augmentation to reduce overfitting, as we have these tests where we say train on Keras code examples and the API documentation, and then we want to evaluate the model in the Keras developer guides. We think data augmentation in the form of synonym replacement and then using generative models to append to these data sets could be a really great strategy to reduce overfitting. In general, we're always looking to collect more data. So we're renaming our data set in future work to DL CodeWiki, although we haven't completely determined this title. And we're trying to add data from the PyTorch documentation, Medium, Stack Overflow. We're trying to really expand the size of our data set. Then we're looking into retrieve then read modeling. So rather than just having this language model that only has the current input as its context for its current input, we're going to have an information retrieval component of this that's shown in papers like Realm or Retrieval Augmented Generation, and we're going to use a vector search engine to retrieve context that will facilitate the current inference. So say it's being asked a question about the reptile paper from OpenAI, it would help to have some information from that paper within the context as well, and we're developing systems that can automatically retrieve that additional context. We further think that tokenization is a big limitation of this. So we're looking into, say, character level tokenization and recent breakthroughs in using these kind of methods. And then as a ambitious project and what we're working on in the long term, we want to connect KerasBERT to a cloud runtime. We want to have a test-driven development debugging system where we train our models with reinforcement learning and some tests that we want to see it perform, like starting to run the model.fit, and we see it starting to fit the data if we have some kind of error in the model setup. So we want to kind of use this reinforcement learning framework to fine-tune our KerasBERT debugging algorithms by connecting to actual GPU cloud runtimes. So overall, we think this KerasBERT framework can be a very useful technique for developing future deep learning code. Thank you so much for watching our presentation of KerasBERT modeling the Keras language. More than anything else, we think the novel contribution of this work is to highlight this data set, highlight the early results of fitting data sets like this, and then overall illuminate this application of using language models to not only just write code, but to write deep learning code. And we think this can massively improve deep learning developer productivity, researcher productivity, and experimentation time, and particularly help with debugging with new ideas that are trying to be implemented in Keras. And for future work, we aim to derive information from all across the internet and wherever we can find it to try to add more information to this debugging. So thank you so much for watching our presentation on KerasBERT. I really hope this inspired your interest in using language models to model code and deep learning code datasets.